Hi, my name is Lauren Barger, and today I'll be presenting Lab 3, Magnetic Field of a Bar Magnet. This lab report will have three main sections: the introduction, which will cover the purpose, concepts, and results; measurements and calculations, which will cover the data, observations, and calculation results; and finally the glow script model, which will cover the code and the visual model created for the magnetic field of the bar magnet. Let's begin with the purpose of the lab, fundamental concepts that were included in the lab, and a quick look at the results. The purpose of this lab was to gain a better visual understanding of magnetic fields and how distance can affect the magnitude of the magnetic field. Fundamental concepts of this lab include the Biot-Savart law, which will allow us to compare the distance-dependent measurements in this lab. Another concept is the distance dependence equation for a magnetic field. This equation can be written in two ways, as seen on the left. Results for this lab included that n was equal to negative 3.4896 meters, and the magnetic dipole was equal to 1.16 amperes times meters squared. Next, let's talk about the data collected for this experiment, along with observations as well as calculations needed for the lab. The data collected was obtained by using a magnetometer on a smartphone device. The data in the top left-hand corner shows measurements for the magnetic field on axis, while data on the bottom of your screen shows measurements for the magnetic field off-axis or perpendicular to the bar magnet. Both data tables give an average of the magnetic field at each location, but only the values of average distance and average magnetic field for the on-axis values were linearized and then plotted. This equation will come in handy when we calculate our results. Before we get into the calculations, I want to discuss some of the observations I made while gathering my data. I noticed as the magnetometer moved closer to the magnet, the x component of the magnetic field increased, and when the magnetometer is far away from the magnet, it measured a near zero magnetic field in the x direction. Another observation I thought was important was that the B Earth value must be subtracted from the measured y value in order to get a value for the Earth's magnetic field. For our calculations, I used the distance-dependent equation that we obtained from the graph where we plotted the linearized magnetic field against linearized distance. Taking this equation, we can use the slope of the line, which is negative 3.896, as our end value. We then apply the Biot-Savart law to calculate the magnetic dipole moment. First, we solve for the value of k by plugging everything we know into the linearized form of Biot-Savart's law. We know from the distance-dependent equation that Bx is equal to negative 15.27, and by using the value of r is equal to 1 meter, we can solve for k, which ends up being 2.335 times 10 to the negative 7. Next, we set the magnitude of B bar equal to mu naught over 4 pi times 2 mu over r to the third. By subbing in k times r to the n in for B bar, we can plug all of our known values and solve for mu. This value ends up being 1.167 ampere meters squared. Finally, let's go over the code that went into creating our visual model in GlowScript, as well as the visual model itself. Here you can see the main parts of the code that went into creating the visual model. As you can see, the code's backbone includes a function for the magnetic field. This allowed us to create what a magnetic field would be due to a dipole at a particular location. There were also 2 axis locations, as well as 4 perpendicular locations that were added to the code as our observation locations. Each of these locations had its own calculated magnitude, as you can see for r-axis 1 and r-perp1 on your screen. Finally, to calculate the magnitude at an observation location 45 degrees from the axis, the d perpendicular value was input into the dipole function to obtain a value for this location. For the visual model, the purple arrow shows the magnetic field on axis, the cyan arrows represent the perpendicular magnetic field, and the green arrow shows the magnetic field at a 45-degree angle. From this angle, you can only see 3 cyan arrows, but given the output on the right, we can determine that there are 4 cyan arrows visualized. Since all perpendicular arrows have the same magnitude and direction, the cyan arrow at the middle of the screen is just perfectly overlaid on top of the 4th cyan arrow behind it. Before we conclude this lab, I want to talk about what would have happened if things had been a little different. For example, if we had laid out the meter stick at some indeterminate angle with respect to the Earth's magnetic field would have interfered in our experiment, and the x direction would not have been 0t. By taking into account magnetic north in our experiment, we were able to ensure that the x component started at 0t. I also want to talk about how if we would have added another magnet that was identical to the first and placed the two end to end, The value of the magnetic field would have been more than the value we obtained from the lab, but the value may not have been completely doubled. So in conclusion, we were able to calculate the distance dependence in magnetic dipole of this system by applying the Biot-Savart law. And through this, we were able to visualize how the magnetic field behaved. Thank you guys so much for listening, and I'll see you all next time.